Finding a good match, coloring and matching. Introduction. A cellular phone company provides services on 3 different frequencies. They expand into a new area and they plan to build 10 communication towers there at locations already selected. Each tower will broadcast signals on the frequency only. The company has to make sure that the distance between any 2 towers broadcasting on the same frequency is more than 50 miles. Let us decide knowing the exact locations of the towers if this is possible. In other words, whether a proper assignment of frequencies exists. How can we translate this problem into the language of combinatorics? The reader probably conjectures that we will somehow find a graph theoretical representation for this problem, otherwise we would have brought it up in this chapter. The natural candidates for the vertices of the graph G representing a given set of towers are the towers themselves. And when should 2 vertices be connected by an edge? There are only 2 kinds of pairs of towers for the purposes of this problem. Those whose distance from each other is at most 50 miles. Such pairs of towers cannot broadcast on the same frequency, and those whose distance from each other is more than 50 miles. Such pairs of towers can do so. Therefore, it is plausible to define the edge set of G by requiring that there be an edge between A and B if and only if the distance between the corresponding 2 towers is at most 50 miles. Fine, you could say we figured out how to express all relevant information about the distances between our towers by a graph G. However, does this help us decide whether the frequencies can be assigned to the towers in a proper way? After all, G does not contain any information about different frequencies, not even their number. This is a valid concern. So that we could incorporate more information into G, we will color its vertices. If frequency 1 gets assigned to a tower, we will color the corresponding vertex red. If frequency 2 gets assigned to a tower, we will color the corresponding vertex blue. If frequency 3 gets assigned to a tower, we will color the corresponding vertex green. And finally, if frequency 4 gets assigned to a tower, we will color the corresponding vertex yellow. Now the following proposition is the direct consequences of the definition of our graph G, proposition 11.1. Let C be any set of 10 towers, and let G be the graph defined by C as described above. Then one can assign the 4 frequencies to the 10 towers of C if and only if it is possible to color the vertices of G with 4 colors so that there are no 2 monochromatic vertices that are adjacent. The following definition provides a simple way to describe how difficult it is to color the vertices of a given graph without creating adjacent monochromatic pairs. Definition 11.2. The monochromatic number. The chromatic number of a graph G, denoted by chi of x, is the smallest integer k, for which the vertices of H can be colored by k colors, so that adjacent vertices are colored by different colors. If the vertices of a graph can be colored by k colors so that there are no adjacent monochromatic vertices, then that graph is called k-colorable. Example 11.3. The chromatic number of the pentagon is 3. Indeed, 2 colors do not suffice, while 3 colors do, as shown in figure 11.1. All graphs in the remainder of this chapter are assumed to be connected. This will not result in any loss of generality, as colorings of different connected components of an unconnected graph are certainly independent from each other. Similarly, we can assume that our graphs are simple, as adding one or more new edges between the same pair of adjacent vertices does not impose any new restriction on those two vertices. They could not be the same color anyway.